Hello, and welcome back to our fourth example of optimization from section 4.7 in our calculus textbook. This one is another exercise from the book. It's number 55. And so we've got a boy and man named Brandon on one side of a river. We're told that it's 50 meters wide, and he wants to get across the river and 200 meters downstream as quickly as possible. And he's going to do that in two ways. He's going to swim diagonally across the river for a while, reach the other side, and then run the rest of the way. So we're trying to figure out what is the best route if we're told how fast he can swim, 1.5 meters per second, and how fast he can run, 4 meters per second. And so we want to think about what this find the best route means here. And so to get someplace, I guess we have another tip up here, this phrase, as quickly as possible. So when you do something quickly, you're doing it in a lesser amount of time. And so what we're trying to do in this case is our goal is to minimize the total time T it takes Brandon to reach his destination. So I'm going to call capital T the quantity that we want to optimize here. And so we've got a sketch, and I've got a sketch in mind here. So I've got a river, and we're told that it's 50 meters wide. I'm going to put Brandon right here, and here's Brandon's destination here, and I'm told that distance is 200 meters. And so the idea is that Brandon is going to swim across to some unspecified point, I'll just call it X, and then he's going to run. So he's going to swim this way, and then he's going to run the rest of the way to his destination. So this is the picture that I think we want to have in mind for the moment. And so the question is, what are the other variables that we have in mind, or that we need on hand in this case? And so I'm going to point out that this point right here is actually a pretty important point. And rather than call that, so if I call that point X, I can also think of this distance right here we'll call that distance X. And so on one other variable is going to be the distance between the point opposite Brandon and the point where he swims to on the other side. And then the other thing that we have is the distance that he runs. I'll call that Y temporarily. And that's going to be this distance right here. So I've got these two other variables. And I want to do the constraint this time first. And hopefully we can see what the constraint is pretty quickly, that this distance X and this distance Y have to add up to the 200 meters that he's going to be traveling downstream. And so our constraint in this case is X plus Y equals 200, or y is equal to 200 minus x. And so I'm going to put that in here, that y is equal to 200 minus x. So what that does is right off the bat, it allows me to think of things in terms of just this one additional variable, x. And so we have to work a little hard to get the objective equation this time. And I want us to remember that this the bit of formula from our high school algebra experiences, that if we've got something that travels at a constant rate, then the distance that it travels is going to be the rate at which it's going, that constant, times the amount of time that elapses. Or distance equals rate times time, d equals rt. I have a feeling you've heard that equation before. And so if I divide both sides of that equation by rate, I get that the time it takes you to do something, if you're going at a constant rate, is how far you traveled divided by how fast you go. So time is equal to distance times rate. And so what I want to keep in mind in this case is that t is going to be the time spent swimming plus the time spent running. And so what I need to do is I need to figure out how long Brandon spent swimming and how long he spent running. So I'm going to come back up here and think about this diagram a little bit more. And so let's let ds be the distance swum, and we'll let dr be the distance run. Hopefully, we can see that the distance run is 200 minus x. So that's not too difficult to figure out. The distance swum is going to come from the Pythagorean theorem. So we're imagining this as an ideal river. We've got a right angle right here. And so the distance swum is going to be the hypotenuse of that right triangle. And so the distance swum, ds squared, is going to be equal to 50 squared plus x squared. So let's check that out. One leg of my right triangle is 50, the other leg of my right triangle is x, and so if I take 50 squared plus x squared, I'm going to get the distance swum squared. And so ds then is going to be the square root of x squared, and I'll go ahead and square 50 out. That's x squared plus 2500 underneath the radical there. And so the rate of swimming, we were told, was 1.5 meters per second, and the rate of running was 4 meters per second. So I've got my distance, I've got my rate, so the time spent swimming is going to be the square root of x squared plus 2500 over 1.5. And the time spent running is going to be equal to 200 minus x over 4. So my objective equation then is t equals the square root of x squared plus 2500 over 1.5 plus 200 minus x over 4. So I've gone earlier in another semester, I went ahead and wrote up the rest of the solution to this problem. And so I'm going to continue on with a scan of a solution I worked previously. The first part of it recaps everything that we've done. So let's talk through this. So I want to minimize the travel time, t. I've got my diagram here. Matches what I had done before. I've labeled x as the distance from the point opposite Brandon to the point where which he swims to, and then y is 200 minus x, the distance that he runs. And I mentioned that's the constraint equation already. And we've gotten down to right here. The time is the square root of x squared plus 2500 over 1.5 plus 200 minus x over 4. And I didn't comment here yet about the domain, but I'm claiming that the domain is going to be x is between 0 and 200. We're going to assume that he doesn't swim backwards up the river. So x equals 0 would be if he swam directly across, and x equals 200 would be if he swam the whole way. So those are my two constraints: either go straight across or he swims the whole way. And we're looking to see at what should be, see if there's something in between that which would make the total time minimized. So this is my domain. And now I'm ready to use calculus. So I'm going to use the chain rule to calculate the derivative here. So I'm going to rewrite this way in order to calculate the derivative. And then I've noted up here that I could rewrite this as 50 minus 1/4 x just by separating the numerator out. And so if I take the derivative, I get 1 over 1.5 times, and we can think about, maybe I should write this instead as x squared plus 2500 to the 1/2 power. So then I can see, using the chain rule, I get that the derivative is 1/2 x squared plus 2500 to the negative 1/2 times the derivative inside part, 2x, and then the derivative of 50 minus 1/4 x is just negative 1/4. And if I think about 1 over 1.5, that's 1 over 3/2, which is equal to 2/3. So this 2 cancels with that 2, and I get 2/3 x over the square root of x squared plus 2500 minus 1/4. To find the critical number, I set this equal to 0, and so if this is set equal to 0, I can add 1/4 to both sides to get this, and then I can cross multiply. I get 2x times 4, or 8x, equals 3 times the square root of x squared plus 2500. Now if I square both sides, I'll get 64x squared equals 9 times the quantity x squared plus 2500. I distribute. Here I get 9x squared plus 22,500. I subtract 9x squared from both sides. That gives me 55x squared equals 22,500. I'll move to my highlighter. And so if I divide by 55, I get x squared equals 22,500 over 55. If I take the square root, x squared is approximately 20.2 meters. And so here I'm going to use the first derivative test as a way of testing to see whether I've got a local minimum or not. So these are my test points, 10 and 30. If I put 10 into, so I'm coming back up here for my so this is my derivative expression, so I'm going to evaluate that at 10 and at 30. And so I'm going to get 20 over 3 times the square root of 2600 minus 1/4. If you evaluate that, you get a negative number. And if you put 30 in, you get 60 over 3 times the square root of 3400 minus 1/4. That turns out to be a positive number. So I'm going from decreasing to increasing, which means by the first derivative test, I've got a local minimum here. And I'll just point out, since this was the only critical number, that means that this is the only place where I switched sign, where the derivative can switch sign, so therefore this is going to be the only minimum, which means that's an absolute minimum as well. And then we go back and think, well, if x is 20.2, y then is going to be about 179.8. And so I answer my question by saying that Brandon should swim so that he lands 20.2 meters downstream and then run the remaining 179.8 meters.